Yes.
That's what we have.
Yeah.
Do you have enough chalk?
Yeah, chalk. Oh, let's see. Sí, ponía como 10 This one is completely wrong.
This one is completely wrong.
Okay,
Yes.
yeah. Okay.
Do you want to watch?
Yeah, you have it.
It's not even used. Yes, you can go for something 7 hours.
Okay.
Okay. Welcome everybody for the last colloquium of the year, also the last colloquium of the joint mathematics colloquium between ICMAT, this university, Carlos III and Complutense. Our speaker today is Clara Löh from Universität Regensburg. Clara obtained her PhD in 2007 in the University of Münster under the supervision of Wolfgang Lück. She then stayed there for 3 more years before becoming a professor at Regensburg, where she has stayed until now, or since then. Clara has done several extended visits to prestigious centers. Here I have noted the Hausdorff Institute in Bonn, the ETH in Zurich, the Mittag-Leffler Center, and as well as the University of Chicago, I believe. She serves as an editor of a couple journals. Her PhD, her research career already has led her to supervise at least 6 PhD students that I could find, plus the ongoing ones. Her main research area is geometric group theory, even though she is also involved in formalization of mathematics using Lean and this kind of ways of formalizing mathematics through a computer, or mathematical proofs through a computer. Although I'm not sure she will speak about that today. And so her title today is the dynamical view on gradient invariance of groups. So, Clara?
Yeah, thank you very much. Thanks for the invitation and for the introduction. So yeah, I will not speak about formalization. I will just speak about conventional good old math. And so it's about group theory, more or less. I mean, it's also related to spaces and some other things, but I picked groups because that's easy to start with and there's no technical overhead. So what's the game? So basically, as I said, this will be about groups, but it's not really about abstract groups, because I mean usually these groups, they come from somewhere. So I don't know, pick your favorite thing. Maybe you something geometry or something, or topology, or also algebraic geometry. But it also works in other fields, but then it maybe works a little bit differently. But whenever you have somehow geometric objects, then you associate invariants to them because you want to distinguish these objects. And many of these invariants, they turn out to be groups. Right? Okay, and so for example, you could take, let's say, fundamental group. That's a prominent invariant. Okay, and then you have these groups, but then somehow, okay, you translated your problem into something that's just group theory, but then group theory usually is still hard. So you want to simplify further, so you apply more invariants to that. And usually you want to simplify the problem, so you should end up in some simpler structures. So for example, it could be nice to just get a number. Okay. Maybe non-negative real or infinity or something like that. Okay, so as I said, so I will not talk about like general groups. So if your somehow geometric object is nice enough, so for example, if you have spaces with enough finite covers, many manifolds will satisfy this. I mean, not all of them, but many that are geometrically relevant do this. Then what you get are groups that have enough finite index subgroups. So these groups are called residually finite, and in technical terms, what does it mean? It means that whenever you have a non-trivial element in your group, then you can detect it through a homomorphism to a finite group. So then there exists a finite group and a homomorphism to this finite group such that the image of your element will be non-trivial. Okay. Yeah, so and then what you could do is you could somehow ask for the asymptotic behavior of variance on these finite index subgroups normalized by the index. Okay? So normalized on this system. Okay, so for example, if you have a real valued invariant of groups, let's say up to iso, then what you could do is you could say that if you have a residually finite group, then you again turn this into a number. So I mean, you can do it with any group, but then it doesn't make any sense. So then you can look at the values of your invariant on all finite index subgroups, but you normalize by the index. So finite index subgroup. Yeah, so there's several versions. You can also do it with normal subgroups, whatever. There's a lot of flexibility what you can do, and maybe you could look at the lim sub or the lim inf. But again, there are more versions of this on how to do this. But this is one way of doing it. And then you get a new number, but somehow it encodes how your invariant develops along these finite index subgroups. Okay, so what I want to do now is I want to somehow explain this in one example. So have a concrete invariant on groups that is very simple to state, and do some calculations, and then, yeah, so then there are some questions that arise. So maybe the challenges that are associated with this are, so somehow, of course, the idea would be that you want to compute this right-hand side without first classifying all the finite index subgroups, because somehow this defeats the point of the thing. So, is there like a global description of such invariants, and these invariants, they're typically called gradient invariants. Right, and then you can also start asking other questions like, okay, now I took all the finite index subgroups, but maybe I only want to look at a smaller subsystem of finite index subgroups. Maybe I only want to look at residual chains or something like this. And then, well, I mean, do the values, will they depend on this or not? I mean, what happens, right? So, so you could ask like dependence on subsystems of all finite index subgroups. Okay, and of course the hope is that at least in certain cases you somehow can do this and get some additional information. Okay, so as I said, I will now do this for one example of an invariant, and I will take the rank gradient of groups. and the definition is very simple. So first I will define what the rank is, and then the rank gradient will be the associated gradient invariant. Okay, so let gamma be a group. Then the rank of gamma is, and I will denote it by RK, but this is not uniform notation. Some people also call it D. So what is it? It's just the minimal number of generators that you need to generate the group. Okay, so that's rank, and then you can define the rank gradient. Okay, and maybe for simplicity I just write it as an infimum, but yeah, of the ranks of the finite index subgroups divided by the index. Okay, and of course, like this number might be infinite, and this will give some real number between 0 and infinity. Okay, yeah, as I said, if the group is not residually finite, then this might be a nonsense thing, because, I don't know, your group might not have finite index subgroups at all, and then it's somehow meaningless. But anyway. Okay, so let's do some examples. Okay, so let's do the rank gradient of the integers. Okay, so that's fairly simple, right? Because for the group of the integers, we exactly know what all the finite index subgroups are. Right? So every finite index subgroup is just of the form n times z for some positive n. Okay, so this is the infimum over all n in n. The rank of nz divided by the index. And of course, we know what this is, right? As a group, n times z is just the integers again. The rank is 1. And the index is just n, so this is just the infimum of 1 over n, and this, of course, is 0. Okay. And yeah, by the same argument, like if you take z and take the product with some other group, then you still get 0. Okay, let's do a slightly more interesting example maybe. So let's take a free group. So this is 3 of rank R. Okay. So yeah, now you want to compute this infimum. So yeah, how does it work? Well, if you have a finite index subgroup inside of a free group, then you know the rank by the Nielsen-Schreier theorem. So you know that this subgroup of finite index, it has to be free and of finite rank, and you know exactly what the rank is. And then in the end, what you get is basically the rank minus 1 is just the index. So times the rank of the ambient group. So what you get here is really just R minus 1 in the infimum. So if R is at least 1. And similarly, you can look at, let's say, the rank gradient of the fundamental group of a surface of genus G. Okay, so this would be sigma 2. Okay, you can look at that, and then you know by covering theory that the finite index subgroups, of course, they just correspond to the fundamental groups of connected finite coverings of this surface. And then you can, again, compute exactly what the genus is of the corresponding surface through the order characteristic. And then you can compute also the rank of these groups by hand. And what you get is, in the end, you get that this rank gradient is 2 minus 2. Okay. But in all these cases, somehow, we always used that we knew all the finite index subgroups. Yeah. And that's a little bit unfortunate, right? It's not what we want to do in general. This would be too hard, usually. Okay, could still be like also challenging, even if you know the full classification, but yeah. Okay. So yeah, maybe one more comment. Of course, if you do this process from like taking your invariant and then doing the gradient, of course somehow you have to get the scaling right. Yeah. So not every invariant will work equally well. So for example, if we would have had the idea instead of taking the rank to take the logarithm of the rank, then you can do this. But for every like finitely generated residually finite group set, you will get 0 because the you know that the growth of the ranks of finite index subgroups is at most linear in the index. So somehow if you take the wrong scaling for your original invariant, then you might destroy everything by doing this. But like for the rank gradient, this is the right way to do it. Okay. So yeah, okay. Yeah, as I said, like this is not what we want. So we want to have a more global way of talking about this. And the idea that people had was to use dynamical system to build such global objects. Okay? So second part will be the dynamical view on the rank gradient. And yeah, so now I first have to explain what a dynamical system is for this talk. I mean, like there are lots of versions, and I will take the following thing. So a dynamical system is what? So this is a probability measuring action of a countable group and so this is just to make it nice, everything like so that things play well together. So we want to have a countable group, and the probability space that we have should also be a nice probability space. It should be a standard Borel probability space. But if you don't know what this means, just think of a nice probability space. Yeah, this is like topologists would not touch every type of topological space in the same way. In dynamical systems, you don't want to touch every type of measure space. Okay, so that's what I would call a dynamical system for now. And yeah, so let's look at some easy examples that you know what this means. Okay, so maybe I should also add one more condition so that I don't have to write it every single time. I also want to have that the action is essentially free. So it's essentially free probability measure to certain action. Okay, so let's look at some simple examples. So we could start with the group of integers, and yeah, what's one of our favorite nice probability spaces is the circle with the normalized Lebesgue measure. And in order to make the action free or essentially free, of course we cannot take any rotation action, but maybe we should take an irrational rotation, and then we have an essentially free. Okay. So irrational rotation actions of the integers on the circle, as I said, with the normalized Lebesgue measure. So that's one nice thing that one could do. What else could we do? Well, we have been looking at residually finite groups. So if you have a countable residually finite group gamma, then you could look at the translation action of gamma on what? Well, on the cofinite completion this is a profinite completion. And what's a profinite completion? Well, this is just an object that somehow takes all the cosine spaces of gamma by finite index subgroups into one object. Okay, so this is the, let's say, inverse limit of lambda and gamma finite index gamma with lambda. So you take all these finite quotients, then they are of course connected through the projection maps. You take the inverse limit over that system. So these are compatible sequences or compatible families in these finite things, and then like each one of these things has a finite counting measure. You normalize this to be a probability measure, and then you can combine this into one global probability measure, and then the left translation action of gamma and all these things combines into an action on the profinite completion. So this is a nice dynamical system that you get for free if you have a residually finite group. And because the group is, I mean, you can always build this, but if the group is residually finite, then this thing will be essentially true. Okay, so that's that. Then if you have a general group, you could take the Bernoulli shift action. So the countable group gamma, then you have the Bernoulli shift. So this is, you just let gamma act on sequences indexed over gamma. And that's, I mean, there are lots of versions of this, but you can just as a base space, you can just take a 0, 1 with the probability distribution 1/2, 1/2. And then you take the product space over the whole group, and you act by shifting the sequences. So this is again such a dynamical system. Yeah, and then maybe if you want to have something that's more geometric, so maybe let's say that M and N are oriented, closed, connected, hyperbolic N manifolds. So they're Riemannian manifolds, oriented, closed, connected, just for simplicity. The Riemannian universal covering is hyperbolic N space, or you could also say it's the sectional curvature is constant -1. And then what you can do is you can, yeah, there are several versions of what you can do, but for example, you can let phi1 of M act on the isometry group of H and divide out by the other group. So this will have a finite covolume, you normalize it, and then you can act on it. Something like this. Okay, so it's like in geometric settings, this also shows up. Such systems. So there are lots of these systems, okay? So now, why do we want to do this? Why is this better than just working with the group? I mean, it's more complicated, certainly at first, but now you have more flexibility. So now if you have such an action, somehow you find your group elements again. So these are the elements that are acting, but now you can do new things that you couldn't do before. So for example, you could say, I have my group element, but I now restrict it to a subset. So somehow you can subdivide your group elements into smaller pieces. And in this way, you can define like a dynamical version of the rank, and this is called cost. So let me give the definition. So this might look a bit technical, but it's really, I mean, it's just what I said. I mean, it's a dynamical version of the rank. It's how many generators do you need, but you have to account for the fact that somehow you can now subdivide generators. So let's assume that we have such a dynamical system. Okay, now I have to explain what the generating set is, and they are usually called graphings. So a graphing, so let's call this action alpha. So a graphing of alpha, what is this? So this is a family. Let's call it phi, of the following form. I make everything explicit. Okay, so you have measurable subsets in X, and you have group elements, and then you just act on these sets by translation of this group element. Okay, so far so easy. Such that, and now the condition is so this should generate somehow the dynamical system, or more precisely the orbit relation. So such that R alpha is equal to what you get generated by phi. So I have to define these two things. So R alpha is just the orbit relation. So this is just like every point is in relation with everything in its orbit. Okay, so this is a subset of x times x. And what you have on the, and you only need this like up to measure. And on the right hand side, you have everything that is generated by phi. So this is the equivalence relation on x generated by the following set, namely all x gamma I x, where I is in I, x is in AI, and gamma I is as above. Okay? So the equivalence relation generated by such a set is just the smallest equivalence relation under inclusion that contains this set. Okay? So this is just a way of translating what a generating set is into this dynamical setting. So yeah, that's called a graphing, if you have this. And then the cost of such a graphing is just, yeah, basically you count how many generators you have, but now you have to somehow also take into account that these generators, not every generator should count as one, but they only should count with the measure of the corresponding set. So the cost of such a graphing is just the sum of these measures. Okay, so now you know like how to count generators, and then of course we define the cost of alpha as the infimum of all the costs of graphings for this relation. Okay, and that's just some number between 0 and infinity. Okay, so that's the dynamical sibling of the rank. And yeah, so maybe we try to compute at least one example. Okay, so as I said, it should basically be a generalization of the rank. So yeah, the rank of the group should give at least some estimate for the cost. And that's easy to see that, well, whenever you have a generating set of your group, and you take for the gamma I your generators, and for AI the whole space X, then what is generated by this thing will be the whole relation. Right? So what you get is that the cost of such an dynamical system is certainly bounded from above by the rank of your group. Okay, because that's like the stupid thing to do. So moreover, what you can see is that if gamma is infinite, then the cost will be at least 1, because somehow the feeling is that you have to touch everything at least once. Okay, so you have to make this precise, but you have this lower estimate. So what you see from this, for example, is that like for every dynamical system alpha of the integers, yeah, you get that the cost of this thing has to be 1, yeah, because it's bounded from above by the rank of z, and it's bounded below by the measure of the space, which is 1 in this case. Okay, so so far so boring. Now the key observation is, if you look back at this definition has nothing to do with the group, right? Because like it has something to do with the group, but you somehow can get rid of it. If you do it right, then you see that this definition only depends on the orbit relation. Okay, I mean, so here now the group elements appear, but you can discuss this away. Yeah? So this is not important. You can phrase all of this in terms of the orbit relation if you want, and here you have the orbit relation anyway. So the cost of such a dynamic system depends only on the orbit relation. Okay, and I know this somehow it takes some time to get used to this way of thinking about actions, because this feels very weird. It feels very weird that you should only look at this orbit relation, so what could it encode anyhow? But in any case, this is very interesting, but I mean, there's a large class of groups for which this is very boring, but now you can exploit this. So, for example, as a consequence, you get from this that if you have such a dynamical system, and gamma is, let's say, so it's a countable group, anyway, and infinite, let's say, and amenable. So this is a notion from, I don't know, large-scale group theory. So if you don't know what this is, so for example, it could be virtually solvable. So it could be a group that contains a solvable group of finite index. But the class is much larger than that. Yeah? Then what you get is that the cost of this dynamical system alpha, as I said, I mean, this only depends on the orbit relation. So let's write it as cost of alpha. And now it's a deep theorem by Kohn, Feldman, and Weiss. That in fact, whenever you have such a dynamical system of some infinite amenable group, then the orbit relation will be the same as the orbit relation of some action by the integers. Okay, so this is now ergodic theory that tells you that this happens. But now we know from the above that, well, in this case, we always have one. So this very, very simple estimate gave us something that is maybe slightly surprising if you haven't seen this before. Okay, so of course you can also prove this without doing this step, but I think it shows in principle what the power is of this approach. And these amenable groups in general, they will not have rank 1, right? So for example, z squared is certainly an amenable group, but the rank is 2. Okay, so what has it all to do with the rank gradient? And that's a theorem by Abel and Nicolau. So if gamma is residually finite, then the rank gradient of gamma is the same as the cost of the action on the profinite completion. Well, and then there's this normalization by this one here, minus 1, and it should be infinite. Okay, so the rank gradient can be expressed as this global thing for the action on the profinite completion. So just in short, basically, how does the proof roughly work? So if you look at this profinite completion, then somehow everything would be nice if you more or less knew that everything that appears here is a cylinder set that comes from one of these finite quotients. And then somehow, from then on, you can somehow combinatorially wiggle your way through to translate this in terms of ranks of finite index subgroups. But so this can be achieved because this algebra of cylinder subsets inside this profinite completion is dense with respect to the measure, and it's like an approximation result that shows that this can be done. So that's roughly the relation between the two sides. Okay, so now you can express this rank gradient in terms of this dynamical thing. So in particular, like if we combine all this, then we see that if, let's say, gamma is residually finite, infinite, and finitely generated amenable, then the rank gradient of gamma is zero. Okay, so that's something that you get by combining these two things. Okay, and again, you can also do this by hand. I mean, you can also have a look at these residually finite amenable groups, and then more or less do it directly. So, but it's not entirely true, because what you need is somehow you need good Ferner sequences if you want to do it by hand directly. And then usually the shortest way to obtain these Ferner sequences, I think, is also through dynamical systems. So in any case, I think this is very elegant, and this approach carries much further. So, for example, what you can also do is, for example, you might wonder, if you take two groups, let's say gamma 1 and gamma 2, then you could take the free product of the two, and you might wonder what is the rank gradient of the free product of the two. Okay, and this can be done by hand, but it's already a little bit awkward combinatorially. But now you might want to try to generalize. So you could say, okay, I take the free product over any amenable group, and then you will see. So you can compute this is the rank gradient of gamma 1 plus the rank gradient of gamma 2 plus 1 over the candidality of A. And this, I think the only way to do this in the full generality of amenable subgroups uses this dynamical approach. And so it uses cost, and it uses a computation of cost where you also somehow can compute the cost of such free products. I mean, you have to make sense of this in the setting of these equivalence relations. So this is was done by Papas based on computations for cost of W. And I think in this full generality there is no direct argument, no. So yeah.
What's the free product?
The free product?
Using A.
Okay, so this is the amalgamated free product.
Ah, okay.
Yeah?
Okay,
so it's just to push out of these two, but you require that the
okay.
maps are inclusions. Yeah. Okay. So yeah. Okay. And you can imagine that also I mean, there are also other computations that you can do through this dynamical approach. Okay, so that's I think is very nice. Okay, so yeah, maybe let's move on to other gradients. So now we did everything with the rank, but okay, so that's maybe not the most interesting invariant to look at. I mean, it's interesting, but it's maybe not the thing why people get really excited. Of course, in the end, you want to look at homology gradients. So let's somehow move there. Yeah. And we'll do this in small steps. So Okay, so let's, as a first example, let's do the first Betti gradient. Okay, so how do we do that? So we look at some group, and maybe to make things well defined, let's assume this is a finitely generated. And then again, I mean, it only gives something reasonable if it's residually finite. Okay, so we take a finitely generated group and we take a field. Okay. Okay, I want to define the first Betti gradient. So what can I do? I can look at again my finite index subgroups. Right. This was a bit too optimistic. Okay, so before we use the rank, so the minimal number of generators of my finite index subgroup, of course, again, we will normalize by the index, but now we will do something different, namely we'll take the abelianization of this group lambda. And then, okay, so this makes an abelian group, we can tensor it up to k. So we get a k vector space, and then we can take the dimensions of that over k. And yeah, let's say we take the lim sup of that. Okay, so this will give you a number. And just to prepare what will happen afterwards, of course, many of you will know the abelianization. This is just another way of saying I take the first homology of the group with integer coefficients. Okay, but this is a concrete way of saying it. Okay, so what do we get? I mean, for sure, we will get that this thing. Well, now here you take the abelianization, then you tensor up, you take the dimension. In any case, I mean, the Z rank of the abelianization, like the free rank of this, will be at most the rank of the group lambda. So what you will get is that this is bounded from above by the rank gradient of gamma, and as we've seen, so if gamma is residually finite, then this is the same as the cost of gamma minus 1. Okay, and now one can start asking interesting questions. For example, like so these are open problems. Is do we always have equality? And maybe let's not be completely foolish. Maybe let's say for k equal to 2. Okay. How does this depend on the field? And well, now we always took like all finite index, but maybe you only want to take residual chains or Faber chains or whatever. And then the question is, I mean, do you get the same value for each of these chains? Do you have actual convergence? Is an actual limit? All of these things. Calculation. Any residual chain. These are all open problems. Yeah. Mainly, right? I mean, some of these things are answered, and I will give some answers in a second. Yeah. So as I already said, that yeah, if I if I interpret the abelianization as H1, now of course then I can define the higher Betti gradients, so I can define the general Betti gradients. I can just do this in any dimension, so I can take Bn hat of gamma, and I can take any field. And again, let's do it with the lim sup. And then we take the dimension of the homology in degree n of the group with coefficients in K, normalized by Unix. Okay, and then we have the same, basically we have the same questions, and there are some answers. So let me give some answers. So there's a partial answer. Which is already pretty powerful, but it's not as good as we want it to be. Okay, so it's the following theorem, and I give attributions at the corresponding places. So let n and n, and let gamma be a group of type Fpn. So what does it mean? It means something like finitely generated, but a higher version of that. So don't worry about it. It's a finiteness condition on the group. And yeah, okay. So then we have the following. Okay, so we can look at this Betti number gradient with Q coefficients. Okay, and then if the group is residually finite, so then you can write this as the nth L2 Betti number of gamma, and this is a theorem of Löh. So I will say something about the nature of this thing in a second. And then it's a discovery of Gaboriau that, well, whenever you have a dynamical system, you have this orbit relation, and you can define these L2 Betti numbers also for orbit relations. So you can do this for any dynamical system in the sense that we had before of gamma, and this is W. Okay, so in this case, you have a perfect correspondence between like the gradient side and a dynamical object, and so like these L2 Betti numbers, they are somehow analytic in nature. Okay, so how do they work? Basically, they're just Betti numbers, but instead of taking usual integer coefficients or something like that, you take twisted coefficients, and the coefficients are, now depending on how you want to do, is either L2 of gamma or the phenomenon algebra, the group phenomenon algebra of gamma. So this has like an independent global description. And also, moreover, this works for any chain. Yeah? So also this here, so also works for every residual chain. And there's been a lot of work to relax this, not to take like a little chain, but maybe take subgroups of an ambient group that are somehow much looser in connection. So you could think of lattices of Lie groups, and also there you have such results that somehow you can compute these gradients through a global object that has a completely different description. And also this is very surprising. This is really a dynamical thing, right? You can express this in terms of dynamical systems of the group. Okay, so in this case, all is nice, but so this is only over the rationals, okay? So in particular, like what people are really interested in currently is, for example, doing this over finite fields. And of course, the obvious obstacle is that if you want to do something like this, if you would just want to copy this approach then you would struggle at this analytic position. It's not so clear what the right things are to consider, because yeah, many of these, like somehow, I mean, you couldn't even formulate what the correct algebra is, but many algebras that could come to mind are somehow very difficult to handle. And I think, I mean, Andre knows much better about all of this than I do. I mean, he can perform all kinds of dark magic with rings. Yeah. Okay, so this is, yeah, as I said, for Q, somehow it's fine, but yeah, for other fields, it's maybe not really fine. Okay, and then maybe let's go one step further. So there's another interesting gradient that's around, and that's the torsion homology gradient. And that's the following. So what we can do is, again, you look at the finite index subgroups, and then you look at, again, at hn of gamma, this time with integer coefficients. But now you take the torsion part of that. So now you really, I mean, this is like basically the complement to this one, because this is about the free part, this is about the torsion part. Then you divide, oh, sorry, this is not gamma, this is lambda, you divide by the index. Again, you take the lim sup, for example, or let's say all of them. And, but this has the wrong scaling. So the right scaling is to scale by the logarithm, because somehow this feels like the dimension, right? If you have a finite dimensional thing, then the dimension of that is basically related to the logarithm, so that's the right way to count this. That's the torsion homology gradient. And then, okay, then people are very interested in computing this, especially for, so this is also like open problems are related to calculations of these things, maybe not exactly this, but things related to this, related to, let's say, arithmetic lattices. Okay, so why is this so interesting? So this is basically work of Bergeron and Venkatesh. Mainly goes into this direction. And okay, it's a fact. I mean, I'm not a number theorist, or like I don't know anything about arithmetic, but it's a fact that these torsion parts of homology, they are related to if you plug in the right kind of lattices that somehow come already from number theory, then these torsion parts of homology, they tell you something about the existence or non-existence of field extensions that with certain constraints on the Galois group. And that's why somehow people really want to know what is the like asymptotic of these torsions in homology. So this is why, like, okay, that's why there's an intrinsic interest in computing these numbers, but as on this side, right, there is no global description of this. Or analytic description, and somehow the feeling is that at least if you somehow choose the situation correctly, then what you get out of this should be not related to the Alberti numbers, but to the L2 torsion. But this is all, it's pretty vague. I mean, there is some somehow computational evidence, but actual connections are very high in demand, but not really there. And also, like something like this description by Gobillot in terms of these equivalence relations, it's, I think so far it's really very very far out of reach. Yeah, because I don't know. I mean, it's complicated. So, like on a technical level, if you think about this, like these are dimensions. So dimensions are basically they are traces. Traces behave well under approximations. These torsion parts, this is more something like a determinant if you ignore the kernel. And so that's somehow, that's very behaves very badly with respect to any kind of approximation. So that's why it's hard to get there, and that's why it's hard to just copy these methods. Yeah, I don't know. I mean, so I completely somehow lost the track of time, but I don't know. I could give one more geometric example, if that's fine. And yeah, maybe I should say, so like in one current ongoing project, so we're trying to somehow develop some dynamical language, but we will not really get to this number, but only give upper bounds, because like, really getting to this one is far too hard. But maybe let's do one geometric example, or one geometric context. And it's the following. So this is about a stable integral simplicial volume. And maybe I just give the statement, and then I explain what the terms are. So this is joint work with Daniel Fauser, Marco Morenstein, and Jose Pedro Quintanilla. Okay, and I'll pick a very simple formulation. The result is slightly more general. So if M is an oriented, closed, connected, spherical, so it means there's no higher homotopy groups, 3 manifold. So the 3 is important. We cannot do it in higher dimensions. Okay, so the stable integral simplicial volume, I'll say something in a minute about this, is the same as the hyperbolic volume of M divided by V3. So V3 is just a constant, it's just the volume of the ideal regular 3 simplex in extended hyperbolic 3 space. Okay, so this is a constant. Okay, so the hyperbolic volume, what is it? You take, I mean, you know by now, by the classification of 3 manifolds, by geometrization, that you have your manifold, you can decompose it into different types of pieces, and some of these pieces will be hyperbolic, and some of these, like the other pieces, will have other geometric types, and you only count the volumes of the hyperbolic ones and sum them up. So this gives the numbers, it's like a geometric thing. So what's the thing on the left-hand side? So this one here, this is a gradient invariant. And this is associated with the stable integral simplicial volume, with the integral simplicial volume. And this is basically something that asks, well, if I have my manifold, how many singular simplices do I need to build my manifold? So this is a topological invariant, and then you can stabilize this, so this is with integer coefficients, but then you stabilize along the finite coverings of your manifold, you get such a gradient invariant. And the statement is, well, this has this somehow intrinsically geometric description, and why do I mention this in this talk? Because the proof, well, on the one hand, you need some geometric input, so this uses concrete geometric construction. But what was really key to like being able to do this calculation was to have a dynamical view on this thing, and lots of results on ergodic theory of groups. And so, I mean, at first, like also what we thought was, come on, it can't be so difficult, right? It's just 3 manifolds. We know basically everything. You just sit down and ask somebody that knows something about 3 manifolds, so you write down good triangulations, blah, blah, and then you're done. But, I mean, at least we could not do it at all like that. And somehow it's it's rather involved, but it makes heavy use of this ergodic point of view. Okay, so I'll stop here. Thank you.
Are there questions, comments?
Yeah, so when you were mentioning examples of dynamical systems, lots of examples there of the world, they come from lattices in Lie groups. Is there a natural dynamical system for these types of groups that is not the profinite completion or something?
Yeah, well, I mean, you can, like, what I mentioned for hyperbolic manifolds, you can also do this, like, in more general setting. Whenever you have lattices in the same kind of, in the same group, you can do that. And that
two
would
lattices,
be,
okay.
yeah, and that, like, this kind of coupling would be then a very natural object to consider. But, so the problem always is, then you have something, for example, if you want to compare these things for two different lattices, which is something that's very interesting, then you could take this obvious coupling to relate them. But in order to get back to the gradients, somehow you have to know how this system relates to the profinite completion. Mm-hmm. And this is where you somehow need some non-trivial input from ergodic theory. And like in this case, in this three-manifold case, fortunately, everything somehow works out perfectly. Like everything clicks together. Mm-hmm. But in more general situations, you cannot expect anything like this. Mm-hmm. But that's one of the challenges. So this is why you usually want to have something that's really, in the end, is independent of the dynamical system of the group or something like this. I mean, that's the best case, because then you can switch around between different systems of the same group.
I have a very naive one, maybe. So your dynamical point of view, you are computing lim subs over groups of finite index. But if you consider the group itself as a subgroup, then you could compute just the invariant that you're thinking without normalizing by the index, because then the index is 1. Do you get, if you include that possibility, I mean, is this lim sub sometimes the same number that you would get with the invariant, or the lim sub is always attained at subgroups of very large index? Or is the answer just no?
Like if you think about the case of the rank gradient of the free group,
yeah.
I mean, basically you get back the rank of the group.
Right. That's why I asked.
Yeah,
yes.
So,
in the case that...
yeah. And also, like, some people would also define the rank gradient by taking rank -1, and then divide by the index, because of this proportionality that you have for free groups. But I just didn't want to do it because it looks more mysterious in the beginning, but it's maybe the better version of doing it, and then you could just get back like the invariant for the.
But of course, when you so the point is that this is interesting when you don't know. Like. Right.
The best case is somehow that you can compute these gradients without knowing all the finite index subgroups, right? Without like.
Yeah. Right. But right. Yeah. Okay.
Does the rank gradient of a group with property T vanish?
Yes, I think so. Yeah, because I mean. Because cost has been computed, and it's equal to 1. Oh no! Oh, sorry. I have to be careful. Okay. Actually, I don't know. I don't know. Maybe Andre knows. Because the cost has been computed and it's equal to 1, but it's not known whether these groups are cheap. So whether whether the cost depends on the dynamical system that we use. So I don't know.
I think so.
Yeah, I'm not sure yet. But at least like it's as close as you can get, basically. Yeah. Sorry.
So maybe it's a silly question, but can these invariants compute for the Thompson group? So for instance, the rank gradient.
Well, like depends on like which Thompson group you mean, but like many of them are not residually finite because they are somehow in the business of being simple or almost simple or something like this. Yeah.
So how often do these invariants behave like I would say an Euler characteristic, that is that you can decompose the thing that you are studying and then compute invariants as with adding and subtracting things? I expect that.
Yeah. So I mean, to a certain extent they do, but yeah. So often it's only known if the thing that you glue over is amenable. Then your chances are best. Everything else is like horribly complicated, and I think not really. There's not really not much. I mean, for algebraic numbers, of course, like this, there's a huge toolbox to compute things. But for example, for cost or also for these like stable integral simplicial volume, it's like it gets very bad very quickly. But if what you glue over is amenable, then you still have good chances. But this is because lots of things somehow happen at the same time. So usually, okay, so one thing is that, okay, if you want to have like a gluing thing, like you have two things that you want to glue over, say, some amenable thing. And then, okay, so let's look at the finite index subgroups of these two things, and then you, of course, somehow you get something for the group that you glue over, but you lose a little bit of control, like what you actually get in this smaller group. And for amenable groups, it all doesn't matter because basically it's all the same. But if you have more general groups sitting there, then you don't know how to relate one side to the other. So then you don't even know how these two sides would talk to each other within the small piece. And it's the same also for the simplicial volume thing. I mean, if you have in this case, of course, you're only gluing over two tori, right? So this is fairly simple. And then you know, okay, it doesn't really matter because it's amenable. Whatever you get from the left side and whatever you get from the right side, you can assume it's the same. But in general, you wouldn't know this. You get something from one side, you get something from the other side. You have to make them talk to each other in the smaller thing, and that's very difficult. So somehow you need some kind of statement that, for the thing in the middle, it's independent of taking like whatever chains you take or something like this, or whatever dynamical system you take, and this is not known in so many cases.
Claire, any more questions or comments? Not then. Let's thank Clara again. You saw that they sent us these certificates.